Greetings. Welcome to lesson 26 of Power Systems Engineering. In this lesson, starting with the circuit of lesson 25B, I will show the use of power capacitors to improve the power factor of the load, and we'll go over improvements that result from raising the power factor in terms of increased efficiency and decreased power loss, and of lowering of the voltage drop. Here is the circuit of lesson 25B. The circuit impedances are given. The load impedance is given for one of the three delta loads, and the other two will be identical. Line-to-line voltage of the load is given as 4800 volts. I have assigned this voltage to VAB of the load as our reference voltage between these 2 points. This system was fully analyzed in lesson 25B, and I will not repeat the calculations here. The goal of this lesson is to raise the power factor of the load from its current value of 0.768 lagging to 0.95 lagging by adding power capacitors in parallel with the load impedances. Once the system is set up with the capacitors in place, it will be analyzed and the results will be compared to the answers from lesson 25B to get a sense of the improvements in various key indicators of the system performance. I will use power triangles for the purpose of determining the size of the capacitors that will achieve a load power factor of 0.95. Power triangles were covered in lesson 17. To start, I'm going to need single-phase load powers of the system before installation of the capacitors, and we'll copy those from lesson 25B to the next slide. Here are the real, reactive, and apparent powers of the single phase of the load given here, here, and here. Next slide shows the power triangle associated with these power components. Here is the power triangle. The horizontal line is for active power, and the vertical axis is for the reactive power, 125.9 in this case, and the hypotenuse gives the apparent power of 196.68, or I rounded it to 196.7 kilovolt amperes here. From the power triangle, it's easy to find the power factor as the ratio of the real power over the apparent power. And here is that fraction, real power of the load for single phase divided by the apparent power of the load, again for the single phase. And the power factor of the load without the capacitors come to 0.768 lagging. I will next place three identical power capacitors, each in parallel with one of the three loads. We don't know the size of these capacitors yet, so I'll simply give them a value of C farads. Seen in this picture, they are all the same magnitude, and I'm just showing one of those. Since the addition of the capacitor does not alter the amount of real power, we know that the real power of the combined load and capacitor will remain at the value of 151.1 kilowatts per phase as before. What changes is the reactive power of the combined capacitor and load, and as a result, the apparent power will also change. Having the new power factor of 0.95 and the real power of 151.1 kilowatts, we can find the apparent power From this equation, we know that power factor equals real power over apparent power. In this equation, we don't have the apparent power of the combination of the load and capacitor. And from this equation, we can easily find the apparent power of the load and capacitor combined. I'm showing the power triangle for the combination. Let's find the reactive power of the combined load and capacitor using the Pythagorean theorem. In this lower triangle, this side is missing. We know the base as 151.1, and we know the hypotenuse as 159. And we can use the Pythagorean theorem to find this side, which gives us the reactive power of the combination of the load and the capacitor for a single phase, of course. Here's that equation. Q for the combination equals S squared minus P squared, and we have both of those here and here. S squared minus P squared, square root of the difference, gives us 49.65 kilowatts for this section here. The reactive power requirement of the load prior to installation of the capacitors was 125.9 kilowatts per phase, as seen here. And now we want it to be reduced to 49.46 kilowatts per phase. And that means that the capacitor will need to provide the delta between these two reactive powers. In other words, this portion of the reactive power, which is what we want the original reactive power to be reduced by, delta Q, is what the capacitor needs to provide. So I'm just going to call it Q sub C. Let's look at that difference. Delta Q equals 125.92 minus 49.65, and that comes to 76.27 kilowatts, which is the reactive power demanded of this capacitor here. Power capacitors are typically specified by their rated voltage and reactive power that they will provide at that voltage. So given that the capacitors for this example are fully specified for the application of this example. However, to continue with the finding of the other quantities, we're going to need the capacitance, or at least we're going to need the reactance, the capacitive reactance X sub C, and I'll find both of these in the following pages, both C and capacitive reactance. Here is QC that was just found. And here's the equation that relates the reactive power of capacitors to the voltage and angular frequency and the capacitance of the capacitor. Having all of these other quantities up to here, we can find C from this equation. And C equals QC over V squared times omega in the denominator. Substituting values for the variables on this side, C equals QC that was just found in terms of volt amperes over the rated voltage at the load squared, line to line voltage, times 2 pi times 60, which gives us the omega. And capacitance comes to 8.781 microfarads. We will now calculate the reactance of this capacitor, X sub C, and that's given in this equation. X sub C is negative J times 1 over omega C. Substituting for omega and for C in the denominator, this is the omega part and this is the capacitance in farads. And X sub C comes into negative J 302.1 ohms. Load Z delta and capacitor are in parallel right here. So let's find the equivalent impedance of the pair of them. 1 over Z, I'm going to call the combined impedance of these two to be simply Z. 1 over Z equals 1 over X sub C plus 1 over this impedance here. And once you do the math and find Z, you should get this number here. 137.6 plus J 45.22 ohms is the combined impedance of these two. And here you have it in polar format. 144.9 with 18.19 degrees. Power factor of the combination of the load and capacitor can be found in a number of ways, but since we have the load argument angle, the combined load of course, it's easier to simply find its cosine, which gives the power factor. The other ways would have been to find the current through, which eventually we'll do that, and multiply the voltage VAB times the conjugate of that current. Here is the new power factor, meaning the power factor of the load after the capacitor is installed, cosine of 18.19 degrees, and it comes to exactly 0.95 lagging. And this verifies that the choice of the capacitor was done correctly because it has resulted in the targeted power factor that we were looking for, 0.95. I'm going to need the currents. I'm going to need the line currents, IA, IB, probably not IC, but at least starting with IA, let's find the line current. One approach will be to convert the combined delta connected load into its equivalent Y by dividing Z by 3, as was done in lesson 25 and 25B. However, I'm going to use a different route here to show the alternative to converting between delta and Y. Note that because we have the line-to-line load voltage as 4800, that's given, we can divide it by Z to find IAB. The load voltage, line-to-line load voltage was given at 4800. That is to be maintained after the installation of the capacitors. So we have the same voltage, 4800. And if we divide that by Z, which was found over here, we can get IAB into this branch here. From IAB, then we can find IA because the system is a balanced system and we have an equation for going from IAB to IA. And I'll show that in a minute. So first of all, IAB equals 4800 over Z, and that gives us IAB as 33.14 amps with negative 18.19 degrees. The equation to convert from IAB to IA, the line current here, is IA equals the square root of 3 times IAB, and its phase angle is 30 degrees behind IAB, so That's where this negative 30 comes from. Inserting the value of IAB from here into this equation will give us IA. And IA comes to 57.4 with negative 48.19 degrees of phase angle. Here is a summary of the quantities that we're going to be needing later. Let's find IB from IA. And that's easy enough because we're looking at a positive sequence balance system. So IB is IA with a phase angle that's 120 degrees less. So if you subtract 120 from this phase angle, you'll get the phase angle for IB, and the magnitudes will of course be the same. I'm going to use the KVL to find the line-to-line voltage of the generator, the plus and minus VAB here. We can do that because if we go around this loop, we have everything, all of the voltages are either known or can be found, except for VAB, which VAB then will be found. We can see that VAB equals IA times Z plus a voltage drop across here between A and B, which is already known as 4800, and then minus IB times Z again, minus because of the direction of IB. I have that on the next slide. Here's that loop, and here is the equation for calculation of VAB. VAB equals this voltage drop, IA times Z line, plus VAB and minus IB times Z line. And here it is with all the values inserted for IA, for Z, for VAB, for IA again, and for Z. Excuse me, for IB. This one is IB from here. And the result comes to 5200 volts with 5.57 degrees of phase angle. That's VAB. Voltage regulation, as you know, is voltage at no load minus voltage at full load at the location of the load divided by the full load voltage. And here's the equation for it. Voltage regulation, or VR, equals voltage at full load, which we have. We found it there. Well, actually we're given that because it's 4800. Voltage at no load, which is the VAB, because when there is no load, there's no current passing through the lines, so the voltage drop over the lines is zero, so the entire VAB of the generator shows up at the load. So at no load, the voltage is actually what we just found here, 5200. We only use the magnitudes for this formula. And V at full load is what we were given, 4800. So we have what we need on the right hand side, and substituting those, 5200 minus 4800 over 4800 times 100 to change it into a percentage, and that comes to 8.33% is the voltage regulation. I'll summarize the results and to make room for the calculation of the powers now. Here are the results so far. Single-phase load complex power is found as VAB times conjugate of the current in that load. So VAB between these 2 points, points A and B, times conjugate of IAB. Of course, IAB was found earlier, this right here. To turn it into its conjugate, we change the negative into a positive. And here are the values. 4800 with 0 is VAB. And this is the conjugate of IAB. The complex power of that single phase load comes to this value, which is a complex number written in its Cartesian format. And from that, we can find the real and reactive powers of the single phase combination of load and capacitor. Real power is the real part of the complex power, and reactive power is the imaginary part of the complex power. I just converted them into kilowatts and kilobars. Next, power loss in one of the three connecting lines will be calculated. Let's say for this line, phase A, we take magnitude of the current that was found earlier, 57.4, square it times the Z for the line, and that resulted in this complex power. And again, from it we can find the real and reactive power losses in the lines, in the single line. 6.59 kilowatts, 19.77 kilobars. Now if I sum the powers of the load and the line, that'll give me the power that this generator will have to put out. And for the real power, it comes to 157.7 kW. For reactive power of the generator, it comes to 69.43 kbars. And here they are. Summarizing those results to make some room here. Let's calculate the apparent power of the generator so that we can use it to find the system power factor. Again, Pythagorean theorem. S source equals square root of sum of the squares of the two powers, the real and reactive powers. And that results in 172.3 kilovolt amperes. And to find the system power factor, meaning power factor looking from here into the system, is the real power over the apparent power. And the answer is 0.915 and lagging. I'll next calculate the three-phase real and reactive powers by tripling the single-phase powers that were found so far. Here are the single-phase powers written all in one place. Multiply them by 3, we get the three-phase powers shown here on the right-hand side. And we don't really need the single-phase power, so I'll just remove those and substitute them with the three-phase power. Efficiency is found by dividing the real power consumed by the load divided by the real power generated by the generator. And we have those values, so efficiency equals, this is the load power, real power of the load in kilowatts, and this is the real power generated by the generator. Again, in kilowatts times 100 gives me 95.8% as the efficiency. Now that we have found all of the required quantities after the installation of the capacitor, we can do a comparison with the quantities that were found in lesson 25B for the same circuit without the capacitor. I have that comparison showing on the next slide in a table. Here's that table for the two quantities. Quantities before installation of the capacitor and quantities after the installation of the capacitor. The first thing to notice is the magnitude of the current that has gone down from about 71 amps to roughly 57 amps. Because power changes with the square of current, you can see that the line losses have gone down considerably. If you do the take the ratio of the magnitude of the current after the installation of the capacitor divided by the magnitude of the current before and square it. I've done this ahead. You get 0.6541, and if you multiply this value by the real line loss, real power loss of the line, 30.22, you'll see that you'll get this answer. And if you multiply the reactive power loss before installation of the capacitor by this ratio of the currents squared, you should get this number. That'll give you a sense of how the change in power affects the change in line losses. The other values have also improved. For example, the generator active power generation has gone down from 483.5 to 473. That's because even though the real power consumption of the load has not changed from before installation of capacitor compared to after, but the line loss has gone down. So the active power generated by the generator has gone down. Also, the reactive line losses have gone down. So the reactive power generated by the generator has also gone down from 468 to 208 kilobars. The system power factor, well, the load power factor first, has gone up considerably from 0.768 to 0.95, and that was a design goal to reach the 0.95 power factor lagging. And the system power factor has also gone up from 0.718 to 0.915. Efficiency has improved because line losses have gone down, so we expect efficiency to have gone up, and it's gone up by about 2 percentage points from 93.7 to 95.8. And the voltage drop has decreased. The voltage regulation, which is an indication of voltage drop from source to load, has gone down from 14.1% down to 8.33%. We have reached the end of lesson 26. My name is Fuad Al-Mandi. I'm a PE in electrical power engineering. You see my name and email address and website on this page. The website is own-your-destiny.mylearnworlds.com. My email address own-your-destiny@yahoo.com. If you enjoy watching my videos, please click on the subscribe button and the notification bell. Also, I invite you to visit my website when you have the time. You'll find comprehensive modules on different topics of power systems engineering on that website. Thanks for watching this video, and I hope to see you soon in another one of my presentations.